But since we didn't cover the non-Gaussian likelihoods in the summer school, we thought that it would make sense to start by focusing on that. You there? Oh yeah, I thought you just wanted my commentary on your talk to be recorded. What?
Thanks.
I think you should have that bit too.
Yeah. Is that on? Yeah. Okay, so yeah, I'm Alan Saul, and today I'm going to talk to you about using non-Gaussian likelihoods in combination with these Gaussian processes that we've been talking about so far. So, as Neil said, this is really should probably belong more in summer school because I'm just going to be reviewing existing work, but I'm going to talk about some approximations that we might use in this situation where we've got some inference difficulties by using non-Gaussian likelihoods. And yeah, hopefully it'll give a bit of a soft start to some of you who went to the brewery last night. So first of all, I'm going to motivate the problem of why we might be interested in using non-Gaussian likelihoods, look at a couple of examples of types of data we might want to consider, and then unfortunately by introducing non-Gaussian likelihoods, we lose some of the nice analytic properties that we have when we've got a Gaussian likelihood, and as a result, we have to do some approximations like what Rich was talking about yesterday, but for sparse GPs. So I'm going to introduce a series of different approximations that we might use in this situation, and they have different advantages and disadvantages. So I'm first going to introduce the LaPlace approximation, which is a very simple approximation. I'm then going to introduce the KL method, which is a variational method, which is very similar to what Rich was talking about yesterday, and I guess some more variational methods are likely to come up throughout the rest of the day. So some of this will be review material. I'll very briefly touch on expectation propagation, but I think Rich is going to give a talk on power EP later, so he'll probably give a more thorough introduction as part of that. And finally, I'm going to compare these different approximate methods to consider where they might be appropriate to use and what sort of likelihoods might be appropriate for each one. So yeah, so over the last few days, we've been considering this situation where we've got some data we've observed, and typically we assume that this data has been observed anywhere between negative infinity and infinity. Because we're modeling it, we're saying why is sample from a Gaussian distribution centered around this Gaussian process that we've been focusing on modeling, right? And critically, we've always been assuming so far this corruption that we have of the mean coming from a Gaussian process is a Gaussian corruption. And this won't necessarily always be the case. So here you can see we've got some realizations of what the function is, and the observations that we're seeing are some Gaussian corruption. And we could expect to see observations as far down as here, but obviously they're unlikely as they're quite far out of the 95% credible intervals. So I'm just going to introduce some notation that we've been using so far. So we've got this Gaussian process prior. And this is encoding some of our beliefs around what we think this function is doing. And there's all sorts of different assumptions that you could encode in this thing. So Nicolas was talking the first day about different kernels that you can use which can encode different assumptions. You've got these, you could assume that this function, which is modeling the mean, is very smooth. You could assume that it's periodic. You could assume that it's a little bit rough, but mostly smooth. And there's all sorts of assumptions that you could encode in here. And then this is the thing that I'm going to be focusing on most today. So far, we've been assuming that we've got IID Gaussian noise. So every corruption that we make from this underlying latent function, we're assuming is independent of any other corruption that we're making, right? So the corruption that we put on at one location of a function. Have we got a pen? Yeah. Actually, we can just go back. So the corruption that we would put on top of this function here is the same corruption as we put here, and they're not correlated, the two corruptions that we would do. And as I said, this is making the assumption that the observations that we're actually seeing are going to be anywhere in the real space, but this might not be true for some different data types that you might be interested in, which we'll come on to a moment. But by assuming that this thing is a Gaussian, we have some really nice properties that when we multiply the prior by the likelihood, the posterior distribution that we end up getting is also a Gaussian distribution, right? And we can do all of these nice integrations, and we don't have any issues. We can just write down all of the integrations in closed form, and we end up with being able to make predictions without any extra legwork, no approximations needed. So the likelihood is the probability of some random data being seen, given that we know what the function value is, but it can also be viewed from the perspective of a function. If we have fixed observations, which we typically do, then it's going to be some function of this input, right? So different functions are more likely to give rise to the observations that we actually see. And in this case, it's a function of f, and it doesn't integrate to 1 under f. So far, we've been assuming that all of our observations are some Gaussian. We're going to model the mean of this Gaussian corruption with this Gaussian process posterior we're learning. However, we often want to consider other types of data than just continuous data. For example, we might be interested in looking at count data. So this is data where we're only going to see observations which are 0 or positive integers, and or we might be interested in looking at binary data where we're only going to see values of 0 and 1, and we can't see any values which are between these two values. And we don't really want to be assigning density in our likelihood to these regimes where we could expect to see an observation which is continuous. There's other types of data you might be interested in using non-Gaussian likelihoods for. For example, if you're likely to see lots of outliers, the Gaussian distribution doesn't have very heavy tails, so you might want to use, for example, a student t distribution, which allows for outliers to be seen without completely having to change the function which is there underneath it. So binary data, we only expect to see observations of 0 or 1. And as in logistic regression, which you're probably already familiar with, we're going to model the probability that we're going to see a class 1 with some parameter, right? And in logistic regression, you do this with you've got this linear function which is modeling this probability. Whereas if we wanted to apply this to Gaussian processes, we want to be able to learn what this some function which is representing the probability that we're going to see a class 1 at any particular input point, right? So here we've got can I move this? Yeah. No. Okay. So here we've got some draws from a Gaussian process, but if you want to be able to model the probability that we're going to see an observation of class 1, we have this issue where when we've got a Gaussian process, the Gaussian process isn't bounded to be between any particular values. So if you want to represent a probability, we want this probability to be somewhere between 0 and 1. So we have to do something to this Gaussian process posterior if we want to try and restrict it so that it can represent this parameter which is representing the probability we're going to see a class 1. So there's different things that you could do, as in logistic regression. We need to somehow squash this function which lives anywhere in the real space to be restricted to only having values between 0 and 1. So you could use a sigmoid function to squash every value of this thing to be between 0 and 1, or you could use a probit and have a similar effect. So here we see the posterior distribution of a Gaussian process once it's been squashed through this probit function here, right? So now we can see that the function which is going to model the probability of each class is restricted to being between 0 and 1. And we can see here if we've got observations, so if we've got the function values are always very low, then that means we're very unlikely to see an observation of class 1. We're much more likely to see an observation of class 0. If all of the function values are very close to 1, then we're much more likely to see observations of class 1 than we are of class 0. And if the function values are somewhere in the middle, so around 0.5, then we don't know whether we're going to see observations of class 0 or 1, and we're likely to see observations of either at this particular input location. So we're going to use a Bernoulli likelihood in this case, and we're going to, instead of just using the Gaussian process to model the mean of a Gaussian distribution, we're going to use some squashed transformation of this Gaussian process to represent the probability that we're going to see a class 1. Does that make sense? Okay, so as I was saying, you might also be interested in looking at count data. Count data, you would typically see only integer values or 0. And you wouldn't expect to see a count of, say, 5.3, and you wouldn't expect to see a count of minus 2.5. So again, we're going to use a different likelihood from this Gaussian likelihood, because the Gaussian likelihood says that we could see observations anywhere. And in this case, we're going to use a sort of simplification of the Poisson likelihood for Gaussian processes. So the Poisson likelihood, again, has a parameter which is going to represent how quickly the counts are coming in. So this is called the rate parameter or the intensity parameter. And if this rate parameter is high, then we expect to see much more counts at this specific location. If this rate parameter is very low, then we expect to see far fewer observations at this particular location. And again, we want to use this Gaussian process to represent, for any particular input, what is the rate at which we're expecting to see observations coming in. So just like in the Bernoulli example a moment ago, this parameter has some restrictions about exactly where it can be. So you can't have the intensity parameter to be below 0. So we need, again, if we want to represent this parameter with a Gaussian process, we have to make some sort of transformation to ensure that it stays in a regime which makes sense for this particular likelihood. And so in this case, we need to ensure that the Gaussian process is always positive. And you could use a range of different transformation functions which would ensure this. You could use a squared function, which would, so if we square the value of the Gaussian process at every location, it'll never be negative. Or we can use an exponential, which is what I've used here. So here we've got a posterior, you can see samples from a posterior distribution, which is representing the rate parameter. When the rate parameter is high, then we see many more observations, and we're only expecting to see observations which are discrete. Is that clear? So unfortunately, by introducing this non-Gaussian likelihood, whereas previously we had this Gaussian likelihood, we have this issue where whereas before we could multiply this Gaussian likelihood by this Gaussian prior, we had a nice Gaussian distribution, and then we could integrate over f easily. When we multiply this Gaussian prior by this non-Gaussian likelihood, we now end up with something which isn't Gaussian, right? And that makes this integral is often not analytically tractable anymore. So that means we can't compute the marginal distribution, which is the thing that we want to optimize the hyperparameters of our Gaussian process and the other parameters of the likelihood. And as a result, we also can't, this thing is also no longer Gaussian, so we can no longer just normalize it and represent the posterior distribution, because the posterior distribution isn't a Gaussian distribution anymore. So there's different ways in which you can handle this. You could consider sampling from this and trying to get samples from a true posterior distribution, P of f given y, which isn't Gaussian. Or another common thing to do is to consider approximating this posterior distribution, which isn't Gaussian, with something which is a Gaussian, right? So we're gonna try and work out some Gaussian which captures most of the information which is in this true posterior distribution, but it's going to be a Gaussian distribution, which means we can do other things, like we can do predictions quite easily. So again, in this case, if we wanted to make predictions at new input locations, at x star, which I haven't marked here, but so we've got new input locations that we want to make predictions at, and even if we did have a representation of this, we'd still have this difficulty where we'd have to do an integration over f in order to make predictions. So we'd be left in a similarly difficult spot that we need to handle. So by assuming that we've got some Gaussian approximation of what this true posterior distribution looks like, we can then use this as a surrogate for what the true posterior distribution actually is. And then we can make predictions or approximate predictions using this, this approximation for the true posterior distribution. So throughout the rest of this presentation, similarly to Rich yesterday, I'm going to call the approximation Q of f, right? So this is the approximation to what the true posterior distribution P of f given y is, which is difficult to get a handle on. Okay? Any questions? So the first approximation that I'm going to introduce is the LaPlace approximation. Some of you may already know about this and might have already used it. It's a very simple approximation. So what I didn't mention is when we're making this Gaussian approximation to what this true posterior distribution actually is, we need to choose some means and we need to choose some covariance, right, to represent this Gaussian distribution. Now, it's not immediately obvious how is best to choose these means and this mean and this covariance. And there's different ways that you can go about it. And the approximations that I'm going to introduce throughout the rest of this talk are different approaches to trying to learn what this mean and this covariance parameter are going to be. But we're always going to end up with a Gaussian approximation at the end, right? So the LaPlace approximation is one method in which you can try and figure out what might be a sensible mean and covariance for that Gaussian distribution. And it's quite a simple method in how you go about finding these things. So the first thing you do is you find the mode of the true log posterior distribution. We work in log space. And in order to do this, you have to do some optimization to find this mode, right? So we're going to represent what the true posterior distribution is, and then we're going to do some optimization along this to find what the modal point of this function is. So by taking since we're working in log space, we also need to work out what covariance to use, which is representing the curvature of this Gaussian distribution. And since we're working in log space, we can use the Taylor expansion to get some approximation of what a reasonable Gaussian distribution might be. But we make this approximation of what the curvature is only at the modal point of the true posterior distribution. And that can be a problem, as we'll see in a moment, if the mode of the true posterior distribution doesn't represent where most of the density, what most of the distribution looks like as a whole. I'll show an example in a moment. So we're going to form a Gaussian approximation where we set the mean of our Gaussian approximation to be the mode of the true posterior distribution. And we're going to try and, at this modal point, we're going to try and match what the curvature is at this modal point. So what we come out with is something like this. So we've got this approximation, we've got this true posterior distribution, which we can't represent. We're going to approximate it with a Gaussian distribution with some mean and some covariance. And we're going to say the mean of our approximation is going to be the modal point, which is represented by f hat. And the covariance is going to look like this. So this is the inverse of the prior covariance plus the negative Hessian of the log likelihood, all inverted. Now, if we're focusing on factorizing likelihoods, which is most of the likelihoods that most people consider, then this W is actually diagonal, right? So that allows us to make some computational savings, and it also allows us to write a more numerically stable algorithm for being able to compute this inverse here. So what I didn't mention is, so we're going to consider only factorizing likelihoods, and we're also going to consider only likelihoods that we can write down in closed form. So there are some situations where you won't necessarily be able to compute the likelihood of your data, because you might not even be able to write down what the maths is for it. So it might be coming from some sort of climate model, for example, and we're not going to consider that situation. I think Rajesh later is going to consider approaches to handling inference when you don't have a representation of the likelihood that you can easily use, and maybe you can just get samples of what your likelihood is. Okay? So instead of just waving my hands around, I'm going to show a graphical illustration of doing this LaPlace approximation. So we've got the log prior here. So this is the log of the Gaussian distribution, and I'm going to consider it for a Poisson distribution. So here, note we're only looking at a single marginal point of the function which we're representing. So this is a mess. So if you've got some function, we're only going to look at what's happening at this particular point, right? So the Gaussian assumption from a prior is going to look like this, and then you're going to have some other likelihood here. So this is only for one particular input point x1, which represents the function values, which has function values f1. So this is for a Poisson distribution where we've got an observation that we've seen, which is at this point we've seen an observation of 4. If we add these two things together, then we end up with the log posterior distribution, which I've marked in blue with this dotted line. So this thing isn't Gaussian anymore, and this is what we want to approximate, essentially. So we need to find some way of approximating this. So as in the LaPlace approximation, we start at some point, and then we need to find what the modal point of this distribution is. So we follow some gradients until we get to the modal point, and at this point, we evaluate what the curvature is at this point, right? And then we're going to use that curvature to find a Gaussian distribution which has the same curvature, and the mean is set to the modal point, which is marked as a black line here. Yeah. So if we look at this in not log space, then we've got this Gaussian prior distribution here. We've got this Poisson likelihood here. We've got marked in dotted red and light blue, we've got the true posterior distribution, and marked in magenta here, we've got the LaPlace approximation to what we think the true posterior, or how we can represent the true posterior distribution with a Gaussian distribution. So you can see in this case it's quite good. So we've underestimated how much density we need to give to this regime here, and we've overestimated how much density we need to give to this spot here. But in general, we've managed to capture most of the density which is in the true posterior distribution with our Laplace approximation. So the second method I'm going to introduce is the KL method. The KL method, again, we're going to make a Gaussian approximation to this true posterior distribution, but we're going to go about finding these parameters in a slightly different way. And similar to Rich, we're going to use some variational ideas. So we're going to treat this mu and covariance, this mean and covariance parameters as variational parameters. So these are parameters which only affect how good our approximation is, right? So remember, when we're considering this, the whole time we haven't changed our model. We're only considering how we can change our approximation to what the model is telling us, right? So these variational parameters we can move around, and as we move these variational parameters around, we're going to get a better or worse approximation to what the true posterior distribution is. So we're going to define the divergence measure between these two distributions in this direction. So Rich was talking about it yesterday, and most of you seem to already know what the KL divergence is. So we're going to say what we want to do is we want to try and minimize the divergence between our approximate distribution and our true posterior distribution, right? So this is our task. We want to try and make our approximate distribution as similar as possible with some measure to the true posterior distribution, right? And that's the goal. But we have this difficulty where we can't even compute this thing, right? If we could compute the true posterior distribution, then we'd have no need to do the approximation in the first place. So the KL divergence, I'll very quickly go over it because you guys already know what it is, and we've already been over it yesterday. So it's in general for two distributions, Q of x and P of x. Ignoring it, we're not considering Gaussian processes or anything here. These are just two distributions, but I'm going to consider Q of x being our approximate distribution and P of x being the thing that we want to approximate. So the KL divergence is the average additional amount of information required to specify the values of x as a result of using this approximate distribution Q of x rather than the true distribution P of x. It can be written in the following way, which we'll use in a moment. So we've got the log of Q of x over P of x, all under the expectation of Q of x. Now, two properties that Rich used yesterday and we're going to use again is that the KL divergence is always a positive value. So no matter what we do to Q of x, we're never going to get this KL divergence to go to negative. And it's also not symmetric. So we're going to do the KL divergence in this direction, but it would also be a sensible idea to try and do the KL divergence in the other direction, right? We want to minimize the divergence between the true posterior distribution to the approximate distribution. But we're going to consider this direction specifically. So very briefly, we're going to look at how it changes in response to changes in our approximate distribution Q of x. So here I'm looking at the KL divergence between two Gaussians, but these distributions could be anything. and similar properties would hold in this. So here we've got our true distribution is a standard normal, so it's 0 mean and it's got variance 1. And the approximate distribution that we're starting with has the mean is too far to this side, right? The mean is over at -2, and the true mean is at 0. And we start off having quite a high KL divergence, right? So the KL divergence is 2. As we move the mean, as you would expect, closer to what the true mean is, so the two distributions are diverging less, the KL divergence drops, it gets to 0. And then critically, when you start moving the mean away, it doesn't go negative, right? It stays positive, which is the property we need to use in a second. Similarly, if you start off with a distribution which is underestimating the variance, the KL divergence begins quite high. As it becomes closer to what the true divergence is, it drops and it goes through, and then it begins going up again when you start overestimating the variance. So we want to find what this Q of X, what this approximate distribution is going to look like, and we've just written down Bayes' rule here. So we've got this true marginal distribution which we can't compute. We've got this true posterior distribution which we can't compute. We've got the likelihood which is now non-Gaussian, and we've got the prior which is our Gaussian process prior. So we can't compute this KL divergence because we can't compute this. So, but we're gonna start from here anyway, right? So this is the thing that we really want to minimize. So in the end, we want to try and make this diverge as little as possible from this. That's the overall goal. If we write down the KL divergence like this, using the definition from before, we have a posterior distribution under here. If we substitute in using Bayes' rule for what the posterior distribution actually represents, and we expand out the log slightly, then we have this term, which is the log of Q of F over P of F. We have this term, which is a negative likelihood, or log likelihood, not marginal likelihood, just likelihood, which is our, for example, our Poisson distribution. And then we have this, and both of it, we can compute this, we can compute this. This is a Gaussian that we're choosing. This is a Gaussian which is coming from the Gaussian process prior. This is a log likelihood, so we're considering only likelihoods which we can compute in closed form. And, but we can't compute this guy, right? This is how probable the data is under our model. So, and all of this is under an expectation of F. Note that if we can take the expectations across the sums, and this term is log of Q of F of P, log of Q of F over P of F, all under the expectation of Q of F, which you can represent that, you can recognize that as being a Gaussian, as being a KL divergence between these two distributions. So this is a KL divergence between a Gaussian and a Gaussian, which we can compute in closed form. And then we have this term, which we'll come on to a moment, which is the expectation of the log likelihood with respect to our approximate distribution Q of F. And as Rich said yesterday, this log marginal likelihood doesn't care what F is, right? So when we take the expectation over this, nothing changes about it. Yeah, so we've got this thing, we've got this guy, which we can compute. We've got this guy, which we can compute. If we rearrange the equation, so we've got the log marginal likelihood on the left-hand side, and we've got this KL divergence, which we can't compute here, right? So we still can't compute what the log marginal likelihood is, and we can't compute this. So this is the same equation at the top here. Now, we're going to use these properties that we've been discussing over of the KL divergence, where that we know that the KL divergence is always positive. It's never going to be negative. So essentially what we can say is that since this is an equality here, so the log marginal likelihood is equal to this term plus this necessarily non-negative term. If we threw this away, we know that we know the values that we had here were no bigger than the log marginal likelihood, right? Because this thing can only be positive or 0. Yeah? So what we can do is so this is giving us a bound on what the log marginal likelihood is, right? And we want to try and maximize what the log marginal likelihood is with respect to our parameters which we're allowed to change, which are our variational parameters, mu, and our covariance, our variational covariance parameters, c. So we're going to adjust these parameters such that we're going to try and make these two terms as big as possible, which means that this term must be going smaller, right? So if the sum of these two terms goes big, then, and this is an equality between these two things, then that means that we're minimizing the KL divergence between the approximate posterior distribution and the true posterior distribution, right? And that was what we were hoping to do. We were trying to make the divergence as little as possible between the approximate distribution and true posterior distribution so that we can use this approximate distribution as a surrogate for the true posterior distribution. So this thing is easily computable. You can just write down what the KL divergence is between two Gaussians. This thing is a little bit more tricky. So this is the log likelihood, and it's under expectation of Q of f. And for factorizing likelihoods, it means that each f is the expectation of each. If we've got a factorizing likelihood, then we have the log of a product over individual likelihood terms, which becomes the sum of a log over individual likelihood terms. And then we can compute the expectation for each one of those independently from one another and add them all together. So you can do that either using some sort of Gauss-Hermite quadrature or any numerical integration method that you want. Just standard Monte Carlo integration would be fine as well. So that means this is computable. It's not closed form, but we can do it quite easily just with a series of one-dimensional integrals when we're considering factorizing likelihoods. So in practice, we still have this issue where we have n by n variational parameters. So we've got a lot of flexibility about what we can do, or this needs to be symmetric, so it's less than that. But in practice, you can reduce the number of variational parameters by reparameterizing C in the following way, noting that the bound here is constant in the off-diagonal terms of C, right? So this essentially allows us to reduce the number of variational parameters we have significantly down to only 2n variational parameters. So, like I say, I'm very briefly going to touch on expectation propagation because I think Rich will probably give a better introduction later, maybe, yeah? But so expectation propagation is another approximate method that we could use for approximating this Gaussian distribution, using a Gaussian approximation to the true posterior distribution, right? And EP uses a specific factorization of the approximate Gaussian distribution, and it assumes that you've got this Gaussian prior, which is the Gaussian process prior, and then you've got a product over unnormalized Gaussian distributions that we need to learn some parameters for, right? So we've got some unnormalized Gaussian distribution with some parameters mu squiggle and sigma squiggle. Squiggle is probably not the proper word. And what we need to do is we need to try and change these guys and try and learn what this normalizer term is as well. And you do that with a specific algorithm when you're doing EP. So we're going to iteratively visit each one of these specific I data points, and we're going to consider how we can adjust these parameters such that our approximate distribution is going to become closer to the true distribution. Right, so it's an iterative algorithm. It has some issues with doing this. I'm going to skip over this relatively quickly because, yeah, I don't really have enough. In previous years, we've done an entire lecture on EP, so it might be difficult to get all of the ideas from this, but I guess I can quickly touch on the general approach. So from this approximate posterior distribution, Q of f given y, so from this, we're going to leave out one of these site terms, right? And we're going to marginalize over all of the other f's, right? And that's going to give rise to what's called a marginal cavity distribution. And the marginal cavity distribution is essentially what would the approximate posterior distribution look like if we'd have left out one of these site terms for a chosen I. So we're going to combine this marginal cavity distribution with the exact likelihood contribution, right? So we've got these site parameters which are somehow a sort of local likelihood independent local likelihood functions, and we're going to pull out one and we're going to replace it with what the true one is, right? From this, we're going to try and work out what a unnormalized Gaussian approximation to this. So we're going to define this as Q hat Fi, so the marginal distribution here, is a product between the marginal cavity distribution and the actual likelihood contribution here. We're going to choose an unnormalized Gaussian approximation to this guy. Right? So this isn't Gaussian still because we've got this non-Gaussian distribution, and this is a Gaussian distribution. So we're going to find out what the moments are of this q hat, right? And we're going to take the 0th moment, the first moment, and the second moment. So the 0th moment, the first moment, and the second moment of this. And then we're going to try and modify these site parameters. Oops, gone too far. We're going to modify these site parameters such that the marginal moment matches the marginal posterior distribution matches the same moments as what we've just found here, right? And then we're going to choose another I, and we're going to start the whole thing again. So it's an iterative algorithm. We're going to take one out. We're going to adjust our approximation slightly. We're going to match some moments so that we've changed our approximation, and then we're going to go on to the next data point. I'll skip through this. So finally, I'm going to very briefly touch on comparing these different approximations that we've been talking about. So we've got the LaPlace approximation, we've got the KL method, and we've got EP. And so here we've got a representation of what our prior distribution looks like. So on the function, we've got two values of f, which are highly correlated to one another, right? So if we were using an RBF, this would say that we're looking at 2 points which are very close to one another because we're seeing a strong correlation between these two values, right? So this is representing f1 and f2, which are located at input locations x1 and x2 respectively. Does that make sense? Yeah. So that's what our joint Gaussian distribution looks like for these two particular function values, which are jointly Gaussian. And if we consider Bernoulli likelihood, where we've seen at these two input locations, we've also seen observations of class 1 for the first input and observations of class 1 for the second input, right? So this is what the likelihood distribution this is what the likelihood looks like as a function of f. So if f1 and f2 are both high, then it's very likely that we actually saw these. We saw both of the observations being class 1, right? If either f1 or f2 are small, then it's unlikely that we saw both of these observations being 1. So that's the prior distribution, that's the likelihood coming from a Bernoulli or probit. And we know that if we want to compute what the true posterior distribution is, we just multiply these two things and renormalize. This is the thing that we wish we could get a handle on. I've plotted it here in for 2 dimensions, but in practice this is going to be an n-dimensional thing that we need to approximate, right? So I'm only considering 2 input locations where we've got observations, but in practice we're going to have many more than 2 input locations where you have observations. So this thing is going to be some sort of n-dimensional blob that we need to approximate with a Gaussian distribution. So this is what the true posterior distribution looks like. So we can see that it's in the posterior distribution, it's also very unlikely that given the data that we've seen, which is 2 observations of class 1, that we're going to see that either f1 or f2 are very small, right? And from the prior said that it's very unlikely that we're going to have f1 and f2 at infinity because the prior said, okay, we want them to be somewhere smallish, right? So this is the true posterior distribution for 2 inputs that we want to approximate, and this is what we get from a Laplace approximation, right? So in the Laplace approximation, we find what the modal point is here, and then we approximate that location with a Gaussian distribution by matching the curvature at that point. And we can see as a result of doing this, so here we're only using this this modal point to represent to find out what the curvature is, and we're doing a sort of localized approximation considering only the modal point of the true posterior distribution. And as a result, we're not really considering where most of the density is. So here we can see in our Laplace approximation, we end up assigning quite a lot of density to this regime where f1 and f2 are small, which is this impossible situation, right? f1 and f2 being small is very unlikely to give rise to 2 observation of class 1. And we've also not really been able to capture most of the density which is up here, because we've got this the modal point is not very representative of what the actual posterior distribution looks like, right? This doesn't tell us everything that we need to know about this. Yeah, this is the KL approximation. So again, the true posterior distribution is the same here. And we want to approximate this by minimizing the divergence between our approximate distribution, which is a Gaussian, and this distribution here, which is a non-Gaussian. So the KL method tends to, the KL method has a strong penalization for assigning density where the true density is actually very low. And as a result, it really tries to avoid this regime here where we've got no density, right? And you can see that it's very conservative trying to avoid this area. And as a result, it puts its mode right up here, and it spreads its and it doesn't spread its variance out too far because it doesn't want this to go over here because it gets a strong penalization for having that situation. Okay, and finally, EP doesn't have quite the same penalization. I believe that when you're doing EP, that it has a bigger penalty for not assigning density where there is some density, but not as big a penalization for assigning some density where there is none, right? So it's not quite as conservative around here, and it doesn't mind stretching out its variance a little bit more because it's not a big issue if it puts some density over here, but it's a really big issue if it doesn't capture some of this density here. So this is in contrast to the KL method. This is just a visualization on one dimension, so we can see the three approximations. So we've got this true distribution. So here we're just looking at these marginal moments here up for F1, or the top ones actually. So we can see we've got this true distribution which is skewed. We've got this LaPlace approximation which uses the mode and tries to match it. We put way too much density in this regime here, which is the posterior distribution says is unlikely to happen, the true posterior distribution. We've got the KL method here, which is very conservative about trying to assign any density here in this regime where the true posterior distribution doesn't actually have any density, right? So as a result, it sort of shrinks its variance a bit and just tries to avoid these regimes, but still try and capture as much of this density in the middle as possible. Whereas EP is a bit happier to put some of this density over here because it wants to capture more of this regime over here, which the KL method is missing out. So some of the pros and cons of these different methods. So the LaPlace approximation is extremely fast. However, if the modal point of the posterior distribution isn't very representative of what the distribution is doing as a whole, then it can make quite a poor approximation, as we just saw in this classification Bernoulli example. So you might use this if the mode was well characterized, if the mode did well characterize what the true posterior distribution is. For example, if you're looking at Poisson, if you have large accounts, then the distribution comes slightly more Gaussian, and then you're going to get a good approximation in that case. So the KL method is principled in the fact that we're directly minimizing some divergence between two things that we're interested in, and it leads itself quite well to sparse approximations, so that to sparse extensions, which means that we can start considering much larger data sets, which LaPlace you can do, but it's not quite as natural. However, it's got some cons in that it requires this factorizing likelihood, at least in the way that I've explained it, to avoid. So because we've got this factorizing likelihood, we can do a series of one-dimensional integrals. If it's not a factorizing likelihood, that isn't necessarily the case. And as can be seen in the results that we just saw a second ago on the probit example, it can underestimate its variance and hence appear overconfident. So it's applicable to a wide range of likelihoods, but is known in some cases to underestimate variance. And so you might want to be careful if you wanted to be very conservative about your predictive uncertainty. And I might well use it if I was using it in conjunction with sparse methods. Similarly,
Alan, you got a question?
Oh.
With the KL divergence, if you did it the other way, so you did the divergence between the true posterior and the approximate,
Yeah.
So it penalizes now putting any density where there isn't, but wouldn't it spread where there isn't, so it would have the opposite effect, like a little bit.
Yeah, so EP doesn't exactly do so EP does something similar to doing the opposite divergence, which is this property I was saying about where it's slightly less conservative about putting the density here, but it doesn't exactly do it as far as I'm aware. No, you're kind of doing it when you're doing this moment matching. You're doing this negative divergence, right? Is that yeah? Is that okay?
Yeah, you mentioned earlier, like, oh, you should try both methods.
It would, so in practice, I don't think you can do the opposite divergence analytically like you can in the KL method. So yeah, it would be a great idea, but we can't do it. So EP method, so EP is very effective for certain likelihoods. Empirically, it's been shown to be very effective for classification in particular, and it works on a range of other likelihoods. And it also extends itself quite well to sparse approximations, which I think, are you talking about that? Yeah, power EP, yeah. So Rich will give you more details about how you can use the EP method, not necessarily on non-Gaussian likelihoods, I guess, but for doing sparse things. So it's got the cons. So the standard algorithm for doing it, we've got this iterative method, and it could be quite slow. However, as I said, you can do sparse things with it. If you're considering larger data, then you can do some things to make it work a little bit quicker, or quite a lot quicker. Convergence, it can have some convergence issues for certain likelihoods. So for likelihoods not log concave, I think it has difficulties in that situation. And you need to be able to match the moments, which isn't necessarily a problem, but they can be a bit heavy to derive in some cases for some likelihoods. Although you could probably do some sort of numerical integrations for these as well. So when might I use it? I'd particularly use it if I was looking at a classification case where we've got this binary data, or perhaps if you were looking at some sort of truncated likelihood, like in the survival case. And again, I might use it if I was going to have to consider larger data sets, and in that case, I need to be able to do some sparse extensions to these things, so the LaPlace approximation isn't quite as good for that. And finally, I haven't really mentioned it throughout this presentation, but there's EP methods. So here we're trying to get samples from a true posterior distribution, and in the theoretical limit, this gives us samples from a true distribution. However, it can be quite slow. Lots of people are working on methods which are faster for Gaussian processes. So I might use this if time wasn't an issue, but having exact accuracy in our true posterior distribution was an issue. And it's also quite widely used if we're making up a new approximation scheme and we want to check whether the approximation that we're making is a reasonable approximation to the true thing. Then you might use it as a sort of ground truth to compare it against. Okay, that's everything. Any questions? No? Let's copy here. Yeah?
So essentially, when you're talking about dealing with, so in this system you might have quite a skewed distribution which you're trying to cope with by creating a better approximation for Gaussian. Why is that a better approach than trying to do some sort of more deep learning type approach where you have some sort of another layer where you have tried to model some transformation potentially on top of it? Why is that?
So why do this rather than deep GPs?
Yeah.
Because it's much simpler. Anything else? No? Okay. Coffee?